Welcome to the course on Introduction to Electrical Engineering. We will discuss, of course, we will have a lecture 21 on bipolar transistor part 1. Well, we like to introduce and typically talk about its application, and that certainly encourages why we really have to study this bipolar junction transistor. Then we will talk about the construction, history and construction, and then of course, its basic operation, followed by its configuration, the bipolar junction transistor configuration, followed by numerical problems. So, starting with the introduction, why we really, what the application could have been and why really we are going to typically the Bjt. So, we will like to introduce of course, this Bjt and construction operation, then we will talk about configuration of Bjt with DC biasing, why we need really DC biasing and applications of Bjt as typically in logic gates, edge switch and amplifier, and why it is necessary. The Bjt and the innovation it had to lead have countless application in modern digital world and wide range of application, not limited only to the electronics domain. Well, now about the history, I mean what it has been in the past and what it has replaced this transistor. So, initially during period of 1994 to 1947, thermionic valves, which known at that time vacuum tube, were used in electronic circuit mainly for amplification, and these vacuum tubes functions on emission of electrons from cathode to anode on the applications of current, which generated heat and its work as a like a diode, which we call it today to operate. We discussed already. I mean like so vacuum tube and internal junction. This was invented by J. Fleming. I mean the basic operation, and these are the some of the of course application glowing tube due to the thermal emission. And later on, of course, some modification were made in the thermionic diode. In 1994, DeForest added a control grid powered through external supply and behave as a gate, I mean which are you can see the as a symbol here, and this device was called triode, and first it was the first kind of a equivalent to a device which you call it the transistor, and you are able to control from this cathode, I mean typically the flow of the current so from anode to cathode, like as you can see the symbolic as well as the structure of it like. And these are the some of the examples of low power triodes, I mean starting from 1918 to miniature tube up to 1960, and the triode based modern high fidelity outdoor amplification. Of course, how it has changed this history. December 1947, Dr. William Shockley, on the name basis we even have a diode now, Dr. John Bardeen and Dr. Walter Brattin invented the first transistor in Bell laboratories, and you can see I mean all of them really with the replica of transistor how they really invented first time like that was the really for semiconductor transistor time. And what are the applications today you can think about? One of the major application of transistor is in digital computing, and due to the use of combination of transistor as logic gates, the digital logic could now be created through their application, and the second generation of computing was brought by use of discrete transistor, and you can see how it is a first generation vacuum team, then second generation transistor, then third generation integrated circuit, then fourth generation very large scale, we call it VLSI integration, and then ultra large scale integration for fifth generation. And this leads to the certainly the generation of computer hardware also based on the transistor. That is a one offshoot application of this, you can call it of transistor, semiconductor transistor, or you can call it the transistor which we are using for many applications, especially for computer industries are revolutionized by this transistor in different form. This again was the history based on the transistor. The first transistor computer in Manchester in 1953 and transistor digital computer in Bell Lab in 1954. Then in IBM 7090 a commercial mainframe transistor computer in 1959, and the PDP 80 commercial transistor mini computer in 1965, how they look like I mean. And that was the of course, I have shown you the chip how it is going to computer industry, and now we have a lot of devices which are doing computation. We call it DSP, microcontroller, starting initially from microprocessor, we call it like a microcontroller as well as digital signal processing processors to be used for doing the very fast calculation for real time application apart from your the computer which everybody see today, whether it is a laptop or desktop or mainframe computers like. Now, that was one side of application. This is another side of application of transistor. I mean transistor work as a switch, I mean like as a solid state switch, and the benefit of taking transistor as a switch that it does not have a number of operation fixed. Like if you take any mechanical switch or electromechanical switch or electromagnetic switch, there is a mechanical motion as well as the operation, and that cause the bounce of heat also on the contact and number of the contacts, certainly physical contacts there. So, you have a number of operation fixed there, but in of course, in solid state switch you do not have a number of operations fixed, like it can long for long period with the billions of, you can call it its operations like as a switch like. So, this is the I mean the let us say the kind of BJT. If you keep a base current 0 here, it operates in cutoff region and remain open circuit, as you can see the switch is open, like I mean as it is the photograph shows there. And when you really want to use as a closed switch like to operate the energize the relay here, as you can see it, we give the signal here which allow the transistor to conduct by this pulse, and once it conducts then relay get energized because it get the voltage across it. But when there is no base, certainly the there is no current flowing, so relay remain open circuit. Why freewheeling diode is provided? Because this relay coil is a inductive circuit. So, suddenly you switch off, there should be a path for the current for shorter the period, because there is a stored energy in the relay. I mean, so this is you can call it the condition as a switch to make it on, and that was the off. Okay. Even relay might have operation of fixed number of operation, but the circuit which are operated from the transistor, of course, low power circuit or low current circuit which really energize the relay. I mean there is no limitations of this transistor to work as a switch as far as number of operation are concerned, but relay certainly have a fixed number of operation. But that is the one kind of, you can call it a operation as a switch, but there are plenty of such kind of application today that this transistor work as a solid state switch like also. Now, another application of transistor is in like amplifier. I mean you amplify the signal, I mean like you can see like amplifier, you might have seen the audio amplifier or sound amplifier. So, the signal which you are giving, let us maybe the sound sine wave, you can amplify it, I mean virtually by this amplifier. So, transistor work as amplifier and its gain can be also increased quite substantial like. I mean of course, I mean the amplification is of the signal, but it is getting energy or power from the battery, I mean like. So, the signal which are input, it can be amplified to output many times. I mean most of the equipment in even electrical engineering we consider them as a amplifier, including even like earlier people used to say DC generator, that you give a small field current, it generate the large voltage like or power like. So, this is similarly like you have a power amplifier, audio amplifier module, as you can see that from which you even have a loudspeaker operating. So, that is also we use similar amplifier in those circuit also or speaker and all that. So, the plenty of application like audio amplifier based on all these transistors only. Transistor work as amplify to the signal, which really you have a very small signal, sound signal on which you are probably speaking or you are playing, and it get amplified certainly through this transistor amplifier in this all you can call it the very musical or instrument part like or you can call it like a transistor radio, might have heard about. So, there also we use the even you can call it this called transistor radio. Like so, transistor has been such a popular that even the people call it transistor radio. I mean like so, but it uses the again the transistor as amplifier like, and has a many other component. However, still we call it the transistor radio like. Another application of course, in the power industry is for the to amplify the gain, we call it Darlington pair. So, where we connect the two transistors in cascaded manner, because the gain of the transistor when you operate as a switch, the gain is quite low. I mean, so, to again increase the gain, then certainly you cascade another transistor which work in amplification mode, and you can get a I mean the gain multiply of the both the transistor stage. That is the virtually Darlington pair transistor used in a power circuit used as a switch, and that is used in power regulator, or it is also used like typically in motor control. This as a transistor switch, you can see how they are connected as typically for many applications we use this as a switch, little larger power large current switch like. But of course, in this case we will be operating the transistor either in cutoff region or we will be operating in saturating region. Why we operate in saturating region? Because the voltage drop across the device should be ideally 0, otherwise you will have certainly some losses across it. So, it cannot be exactly 0, but it goes to like a VC saturation, that may be typically 0.3 volt or so. But the gain is quite small, that is why we have to take another stage for this as a base drive typically. So, this was the the revolution where we have a Darlington pair in edge bridge circuit, which are used like a single phase inverter, or it also used like a 4-quadrant chopper for motor control also. So, many applications are there where we were using the Darlington pair initially. I mean, it has been quite popular for, I mean, later on of course, the device is changed, that you have a typically kind of a device called IGBT, insulated gate bipolar transistor, but the power stage side is still the transistor Bjt, because it has a specific property of very low power loss, but the gate drive is replaced in place of the transistor by MOSFET, and the device becomes like almost a voltage operated device, because you do not need the any virtually the you can call it any much power signal for getting the MOSFET, like, I mean, so it changed the device shape itself, right, but still the power side is still the Bjt, I mean, like also. And then another applications in oscillators. So, transistor oscillator like a Hartley oscillator, Colpitts oscillator. I hope you understand the oscillator, that it has to give typically depending upon the I mean the output signal, you can have a alternating signal of the variable frequency, I mean from these oscillator, and you can change of course the value of the capacitor as it is shown there, and you can accordingly modify the typically the frequency of this, and it is used in many applications for tuning the frequency of different you can values, like, I mean also. So, another major application is in multi vibrator. I mean multi vibrators of course are different kind. So, first is like typically like a stable multi vibrator which does not have any input, but it is a like a you can call it oscillator. So, it give you of a you design for a particular frequency. So, it give you the like a might be a square wave of a particular frequency which you can adjust by, I mean the component put into the circuit of this stable multi vibrator, where the couple of transistors are used in case of this multi vibrator. Another is a monostable. So, you just give a pulse to it, and duration of the pulse you can set for particular application, that how much duration pulse you need it. So, whenever you will give input pulse, a very short pulse, but you can output pulse can be according to your design, that you can increase the width of the pulse or you can adjust the pulse of this. Then another is the bistable multi vibrator. So, you can have a for switching on you have to give one pulse, and switching off again you must have another pulse, like typically. So, these are the multi vibrators have again have the transistor, and typical circuit of stable multi vibrator you can have with the couple of transistors, how you really I mean get it here as a monostable. So, you give the pulse, and the duration of the pulse in monostable vibrator you can adjust it. So, it consists basically a couple of transistors as you are seeing there, and they go on operating in toggle mode, I mean to really, and I mean even both the transistor can be in a one single chip. Finally, in the there are a lot of chips are available which have multiple transistor into single IC chips also. Similarly, for you have another multi vibrator, that we call it bistable multi vibrator, is also used in computer memory. I mean that you can just give a pulses, and then you get output also as a pulse, as well as the you get a inverted pulse also from giving the pulse to form. So, you get a typically two sets of pulse, one is simple pulse and then another is inverted pulse from this circuit of this bistable multi vibrator. And the third is your typically your stable multi vibrator, I mean from which you can get a typically a frequency which is decided by your RC network, I mean typically from this RC circuit, and you can get a typically even you want to get a variable frequency of output, that also you can attain from this, and you not to give anything input. So, it is gone self oscillating for a given frequency by which you decide by the design of these components like RC component here, like I mean also. Another major application is in the timer circuit. I mean the typical you can see how many transistors are in this timer, and the chip which is made integrated circuit which call it 555. I mean timer IC chip with the internal diagram. So, you have a lot of transistor, you can see it, and this 555 is a very standard chip which can have so many transistors and can do the many job as a timer circuit, like I mean also. And you can design many, like you can design from this even chip, you can design a stable multi vibrator, and you can decide how much should be the duration or frequency of this. I mean, and this is the internal structure of this virtually. You have to put external component, I mean connected between the different pin for the purpose of to decide the frequency and duration, the pulses if we want to develop it, and this is the typical circuit which really complete circuit of this of your 555 chip timer you are using for in a stable mode to as a stable multi vibrator, like, and this is typically again using same single chip. I mean in place of using so many transistors, single chip with the component, you are able to make like this as a monostable multi vibrator, or you are able to have like a typically again with these components you are able to have it is bistable multi vibrator. I mean typically same single IC chip of 555. So, this IC chip have been very popular for many applications because it can serve multiple purpose. I mean for the timing circuits like typically your timer circuits, like or so. So, that is typically the some of the application, not all applications, and that gives reasonable justification why we should study really this bipolar junction transistor. Now, coming to basically the typically construction and operation of this of BJT. So, there are 4 basic techniques have been developed for manufacturing the transistor this BJT, and classification of these techniques are in these 4 types: grown type, grown junction transistor, alloy type or fused junction transistor, and diffusion type or diffusion junction transistor, and epitaxial type transistor like. So, starting from first type, I mean grown junction transistor, as you can see the typical photograph how it is developed, made by drawing the single crystal from the melt of silicon or melted silicon and or germanium. These are the 2 silicon, you can call it semiconductor material from which we normally use in the transistor manufacturing at the moment, but later on of course, many others components are many other elements are also used now. So, silicon germanium impurity concentration is changed during the crystal drawing operation to adding N or P type of atom. I mean in P type you can add the N type or N type you can add the P type for growing this typically the your junction transistor or BJT bipolar junction transistor like, as you can see the typically the photograph. So, the another is alloy type or fused junction, as you can see here in the photograph how it is. So, the center base typically here it is a thin vapor of N type, this vapor, and 2 small dots of indium attached to the 2 opposite side typically here of the vapor, and the whole structure is raised to short time to high temperature above the melting point of the indium and below the germanium, and the collector is made larger than typically so that the collector subtends a large angle as we from the emitter. I mean this is typically the emitter, this is collector, and this is the virtually the base in this typically the developed transistor like. And these are the some of the photographs of your alloy type of fused transistor of different types like. And the third is of course, the diffusion junction transistor, just how we diffuse the virtually N type, P type over the and then typically the N type in making of this kind of function where you can see collector base and emitter for Npn transistor. So, this transistor consists of subjecting semiconductor vapor to gaseous diffusion of both N and P type impurities to form both emitter and collector junction, and the base collector junction area is determined by diffusion mask, and emitter is diffused on the base of the different mask, and thin layer of silicon dioxide is grown over the entire surface. So, that the aluminum contact can be made for the emitter and base leads, as you can see here how the diffusion transistor is really there, and these are the typical example you can say how they look like as a diffusion transistor like. So, the fourth one which are quite popular finally, I mean this is epitaxial transistor, as you can see here. I mean so the technique consists of growing very thin high purity single crystal layer of silicon or germanium of a heavily doped substrate of the same material, and the crystal from the collector on which the base of emitter may be diffused, as you can see here, and this greatly improve the device speed and performance, and that is the reason this technique is quite popular for manufacturing or developing the BJT like. So, these are typically the and this is the kind of the package which of using this technique like I mean different package type of BJT are developed like starting from this two. So, now coming this with 4 type of the technique which are used for manufacturing the BJT, and of course, the last one is supposed to be the one of the best. And now coming to the BJT operation, a bipolar junction transistor behave like a triode made of semiconductor material, and junction transistor consists of silicon or germanium crystal in which N type silicon can be sandwiched between the 2 layers of P type of silicon, and it is also called Pnp transistor, and the P type silicon can be sandwiched between the 2 layers of N type silicon that called Npn transistor. These are the 2 kind of the configuration of the transistor, and it is a 3 layer semiconductor device like. And you can just have a 2 kind of configuration of this. This is Npn. I mean you can see the dimensions also how it is the total dimension of 0.15 inch and 0.001 inch that opening in between of N, and this transistor we call it like Pnp, as you can see the symbol here. On emitter we have arrow going in. So, this represents like we have a typically of Pp and base is typically N doped here with the biasing. I mean you just find the biasing, the you can call it forward biasing, and here it is the negative biasing, like negative biasing means the P is connected with the negative voltage and here P is connected with the positive voltage. So, this is for PNP and this is NPN, collector, base, emitter. These are the 3 terminals known in the transistor, collector, base and emitter, and here it is in the same dimensions. Now, these dimensions day by day are reducing to have a very large number of transistors for a small package, like, and that is the technique considered that of how the transistor packaging. So, here again we have a like typically NPN, and here you can see the it is also again forward bias with the you can call it negative connected to negative, and this is your reverse bias when positive voltage is connected to the your N, and of course, base is typically with the P. So, it is called your typically NPN with the DC biasing, like. So, the basic operation of the transistor will now be described using the PNP transistor. Of course, you can discuss with any one of the two, but this is just to explain the operation of the NPN transistor is exactly the same if the roles played by the electron and hole are interchanged, and now we will understand the operation of the PNP transistor. So, this is typically PNP transistor, that this junction your typically emitter to base junction is forward bias, and then C to B is the your reverse bias, like. So, coming to typically the forward bias, to explain it, forward bias in the figure PNP transistor has read on without the base collector bias this side, and depletion region has been reduced in the region due to the applied biasing, resulting in a heavy flow of majority carriers from P to N type, from P to N type material, because this will have a flow of it, because you are connecting a positive terminal. So, from positive terminals virtually whole move towards this region, from this being a forward bias also here. So, majority carriers move, whole moves from this side to this side, like, and this is typically the reverse bias, keeping the. Now, let us now remove the base to emitter bias of the transistor as a shown, and consider the similarity between this situation and that of reverse bias diode. So, recall that the flow of majority carriers is 0 now, and resulting only the minority carrier flows as indicated here. So, it is only minority carriers flows into, because you say with the positive polarity connected there, like also. So, this we call it reverse biasing, like as you can see the P doped material is connected with the negative polarity, that is why the minority carriers only move in this direction. So, in the summary we can say one PN junction of the transistor is reverse bias, and where the other is forward bias, and equivalent diode model is analogy to the transistor to decide to diodes can be represented as seen here. So, you can have a NPN here, and we already told that okay, this is your forward bias, this is by reverse bias, that is why the symbol of diodes are here. Similarly, here it is we call it upper is a in NPN is upper is a forward bias, that is why the diode is shown in this, and this is reverse bias. So, it is shown with the reverse diode, like. So, this is NPN and this is PNP transistor. Of course, NPN are more in practice, like. So, now coming to in the figure here, you can just again have a PNP, and we have this as a forward bias, this as a reverse bias, and this is how it is the depletion and how the majority carrier moving here and how the minority carrier are moving there. So, in figure both biasing potentials have been applied to a PNP transistor with the resulting majority and minority carrier flows indicated, and note that the width of the depletion region indicating clearly which junction is forward bias and which is reverse bias. A large number of majority carriers will diffuse across the forward bias PN junction into the N material. This is the majority carrier which get diffused into the N, like that is the meaning majority and minority carrier, how it is flowing into the PNP transistor. So, here it is a majority carrier, that is why a big arrow, and it is a small arrow because of minority carrier, because of reverse bias this is for forward bias. And the sandwich N type material is very thin and has a very low conductivity, and a very small number of these carriers will take this path of high resistance to the base terminal. So, the magnitude of the base current is typically on the order of microampere as compared to the milliampere for the emitter and the collector current, like. So, typically the large number of these majority carriers will diffuse across the reverse bias junction into the P type of material collected at the typically on the collector terminal, and applying the Kirchhoff's law in this typically the circuit, we say I E emitter current equal to I collector current, this current plus the I base current. A small current flows here, but another current flows here. So, collector current is equal to current due to the majority plus minority flowing. So, this is we can call it I c equal to I majority plus I CO minority, that is the typically you can call it the kind of open circuit terminal minority flowing into there, and this is typically we can call it the forward bias of EB. This junction causes electrons to diffuse from the emitter to base, and as the base region is very thin, the majority of the electrons diffuse at the edge of depletion region of CB, typically of this junction, and then the swept to the collectors by the electric field or the reverse bias junction of this one like so. Now, here we can say what is typically the IC will be alpha times I, because part of the current goes into the base. So, a small fraction of the electrons combined with the holes of base region. So, majority move in this as it is shown in the diagram here. A small only move towards this. So, how holes are also injected from base to the emitter, and the two carriers flow from 1 and 4 typically 1 and 4 typically here from the emitter current, and I C the almost independent of the magnitude of the VCB, and that I C we call it alpha E, where alpha is 0.9 to 0.99 or so in this like. So, this is typically the basic operation. The emitter current flowing into here, a major current goes to the collector side by the gain, as you can see alpha E, and the small current goes to the typically towards the bale, and how your recombination and typically holes and you can call it electrons flow is demonstrated here. So, the emit typically collector current, this is emitter current, and how it is collector current is alpha times I, a major amount current here, because alpha is 0.9 to 0.99, and this is a small current of order of maybe 1 to 10% flows into the base like, and this is typically the concept of basic operation. So, we call it forward active. Okay. VB the forward typically the bias, and VBC is the reverse bias this one, and for reverse active. So, it should be VB the reverse bias as well as VB forward bias, and saturation both are forward bias, then only it will have a small drop and the whole drop will be very small, and cutoff region both are reverse bias, that is means no conduction taking place. So, these are the typical 4 modes typically of the this BJT operation. Depends on application. In some application we might be using, I told you, as a switch we will be operating it as in saturation and cutoff, and but for amplification we will be operating typically in active region also like. So, now coming to like a BJT configuration. So, we have 3 configuration of BJT: common base configuration, common emitter configuration, and common collector configuration. And to fully describe the behavior of 3 terminal device, like working it as amplifier requires the 2 sets of characteristic, one for driving point or input parameters, and other is for output parameters. So, we normally you can call it represent it typically transistor as amplifier. So, this is you can call it the first configuration, common base configuration. Common base configuration means base terminal is common, consider here, and the common base terminology is derived from the fact that the base is common for to both the input and output side of the configuration, and the base is usually the terminal closest or to at the ground potential, and all the current direction will refer to now conventional hole flow rather than electron flow, that the arrow in the diode symbol defined by the direction of conduction for the conventional one. As you can see, this arrow typically kind of representation of this circuit. So, we have a common base here like you can call it. So, just explaining of both how to really work with the common base here, whether it is NPN or PNP, the connection of the two. Here is a common base, but their biasing is certainly have to be opposite. Here emitter is connected with the positive terminal, collector is connected with the negative. Here it is collector is connected with the positive and emitter is connected with the negative, because they are just opposite, and how the symbol is there of and current flow is there from one side to another side. So, here collector current flows to emitter, collector and base current both flows to emitter. Here typically you can say the emitter current flows into the typically going to be to the both with the opposite sign like also. Well, now this is the input characteristic which we already talk about of this common base configuration transistor, and this is the input set for the common base amplifier as shown in the figure related to input current, that is I, to the output to input voltage VB, that is a signal, because base is common. So, we are giving a signal VBE, and from which current flowing into the IE for various level of output voltage. So, here we call it like a VB the output voltage and your I the input current and is the VB the input voltage. So, this is the input voltage, this is the input current and this is the characteristic between two and depends on the your VCB. I mean how much is the really the output voltage, you will get it from corresponding to this in transistor amplifier. This is the input characteristic between IE and VB. Of course, it is affected by the voltage biasing of the VCB like up to some extent. This is the output characteristic. The output characteristic here, the output relates to output collector current, that is collector current to the output voltage VCB, and for the because B is a common, so that is output voltage is VCB for the various level of input current, that is IE or different amount of the current which is getting typically amplified. So, output current, that is IC collector current, and output voltage, that is your VC and the emitter current. So, these are the different emitter current, how the characteristic get modified of this like so, this is typically you can call it cutoff region, this is saturation, this is amplification or active region. So, if you are really want to operate only in saturation and cutoff, then this is the up to how you have to apply the different kind of emitter current and it goes on this region, and otherwise it goes with the different in this region it goes, then it goes to different amount of amplification here like. So, this output characteristic how it look like also, and this output characteristic typically of the common base component, the output collector set of the characteristic has three basic region, I mean which you already mentioned here, active region, then the your saturation region which is shown shaded here, and this is a cutoff region, I mean typically. Now, the output characteristic of the this configuration, we already talked about the output characteristic of the three basic region, active, cutoff and saturation, and active region which is used in many applications like amplifier and all that. The active region, the base emitter junction is the forward bias, where the collector base junction is the reverse bias. So, at lower end of the active region, the emitter current is 0 and the collector current is simply due to the reverse saturation current, and this your reverse saturation current ICO is so small microampere in magnitude compared to the vertical current of your milliampere. That is you can say milli to microampere difference here. So, circuit conditions that exist I equal to 0, that is emitter current almost 0 for the common base configuration because of this almost open. So, we can say ICO, this current will be equal to ICB only because that is the only path of the current can flow, the collector based current with the emitter lag, and as the emitter current increases the above 0, the collector current increases to a magnitude essentially equal to that of your emitter current and determined by the basic transistor. So, we say IC is almost equal to IE with of course, with some factor going to the typically small base current. So, the second output in output characteristic second region is the cutoff region. It defines that region where the collector current is 0, and in the cutoff region base emitter and base collector base junctions of a transistor both are reverse bias, and because of improved construction technique the level of ICBO for general purpose transistor in the low and medium power ranges is usually so low that its effect can be ignored, and at higher temperature the effect of ICBO may become an important factor since it increases so rapidly with the temperature. And the third region is the saturation region for output characteristic of this, and that is you can call it this region where VB will be saturated only 0.7 volt like one is. So, saturation is defined as that region where the characteristic to left of VCB is almost 0 or very small typically you can call it. So, in the saturation region the base emitter and you can call it collector base junction are forward bias. So, input characteristic of reveal that the fixed value of collector voltage as to base to emitter voltage increases and emitter current increases in a manner that the closely resembles the diode characteristic as we see the diode characteristic also. Now, defining a gain we call it alpha gain. So, it is in DC mode as from this characteristic output characteristic here we say in the DC mode the level of IC and IE to the majority carriers are related by a quantity called alpha and defined as alpha equal to IC upon IE, or you can call it IC and IE are levels of current of the point of operation. So, from alpha we can say around 1 and which is but that is practical alpha is 0.96 to 0.995. So, now the BJT current can be defined as follows, that typically relation between your IE, IB, IC current flowing through the emitter, base and collector current from this circuit. I mean, you can say IE equal to IB plus IC, where IC is around 96 to 99.5% and we can say IC equal to your alpha IE. So, major current flows into virtually from collector to, you can call it the emitter, a very small current only flows. The alpha is the emitter to collector gain lies, current gain lies between 0.96 to 0.995 and IC is approximately equal to IE, but due to the reverse bias CB junction, a small reverse saturation current flows and ICBO collector to base leakage current with emitter open circuit, and typically we can say Bjt current IE equal to IB plus IC here. I mean, from this you can call it the Kirchhoff current law relation here, and IC will be alpha IE plus ICBO, and from this IC we can say alpha times IC plus IB plus ICBO, or 1 minus alpha into IC equal to alpha IB plus ICBO, or IC equal to alpha upon 1 minus alpha IB plus 1 upon 1 minus alpha ICO, or we can say IC equal to beta IB plus beta plus 1 ICBO, where beta is your large gain because this is very small quantity. So, beta considered as a large current gain. So, beta is the base to collector current gain assuming no leakage current, and ICBO is the reverse saturation current in the configuration like. So, now coming to now your another configuration which called common emitter configuration. This configuration is quite popular, used in most of the applications. So, in this configuration the emitter is a common to, typically emitter is the common to for base as well as to collector, both input and output characteristic for this, and two sets of characteristic are again necessary to describe the full behavior of the common emitter configuration, one for input or base emitter circuit and other one for output collector emitter circuit like also. So, that is typically you can have a biasing with the of the this input signal which you want to amplify here. So, here you can just see here it is your NPN on which is typically you can call it collector is a reverse bias and emitter is a base emitter is a forward bias, and this is the typical symbol how the current going flowing into the from your collector and going to typically the emitter and with the along base current. This is for your NPN sorry PNP. So, these are parallelly given both the configuration how really the flow of the current can take place. So, this is coming like a characteristic of common emitter configuration. So, two sets of characteristic necessary to describe full the behavior of the common emitter configuration, the input or base emitter characteristic, this we discussed earlier, and output or collector characteristic here. So, you can say this is the collector characteristic. Like, so you have a here VC, that is your collector to emitter voltage, and this is your typically your collector current like, and these are for different base current. So, if it is a base current is 0, then you have a this is cutoff region which is shown shaded here, and in this shaded region where you can have a very small drop of VC maybe around 0.3 volt, maybe small. So, this we call it the saturation region, and this is your active region or amplified region, depends upon the typically order of the base current starting from, you can call it from phi micro ampere 10 microampere to going to 100 ampere, but collector current is milliampere. You can just see how the amplification is there in this case like. So, this is typically the base characteristic, you have a base current and you have a VCB, and this is for different level of the VC voltage like So, so we can say even though the transistor configuration has changed, the collector current relation developed earlier for the common base configuration are still applicable, and the active region for the common emitter configuration is that of portion of upper right quadrant, and that has a great linearity, and that the region in which the curve of IB are nearly straight line and equal to is placed. And this is typically the here again the characteristic between VC and IC with the different base current. So, we can say region exists in the right of vertical dash as a VC saturation, this region to 0, the region to the left of the VC is called the saturation region, and the cutoff for the common emitter configuration defined as IC equal to ICU in this region. So, that we call it cutoff region, this is we call it saturation, and of course, we can call it the characteristic of this VC configuration. So, in active region a common emitter amplifier, base emitter junction is a forward bias, where the collector base junction is reverse bias. So, collector characteristic can be defined here IC equal to alpha I plus ICBO, and IC equal to alpha IC plus IB plus ICO and 1 minus alpha IC into alpha IB plus IC, and IC we can say alpha upon 1 minus alpha into IB plus 1 upon 1 minus alpha into ICBO. So, for IB equal to 0, alpha equal to 0.966. So, you can call it IC equal to 0.996 into 0 divided by 1.9 plus 1 upon 0.96 ICBO. So, you can call it IC will be equal to 1 upon 004 ICB, that is 250 times ICBO. So, for IB equal to 1 microampere, you can call it your IC will be like a 250 times from there, and for ICB 1 and 0, you can call it IC will be corresponding to 0.25 milliampere even for. So, for future reference, the collector current defined by the condition IB equal to 0 milliampere will assign to the notation indicated by the following equation: ICO equal to ICO 1 minus alpha, where IB equal to 0 microampere. For linear least distortion amplification purpose, cutoff of the common emitter configuration will be defined IC equal to ICO. Now, coming to common collector configuration, here typically we call it common collector configuration, where collector is the third and final transistor configuration is a common collector, and common collector configuration is used primarily for impedance matching purpose, which we consider in radio and all that, and high input impedance and low output impedance, and opposite to that of the common base and common emitter configuration. So, this is the typically how it is typically the here the common collector, and you have a typically a forward biasing of the emitter to base junction and base junction to collector junction, it is a reverse bias. So, this is for Pnp and this is for Npn, how it is typically the biasing taking place, but collector is common for both like common also. So, coming to common collector configuration, typically you can just see here collector is ground, because you have to give the signal with respect to this, and so collector is tied to the ground even though the transistor is connected in a manner similar to that of common emitter configuration. The output characteristic of the common emitter common collector configuration are the same as for the common emitter configuration, and for the input circuit of the common collector configuration, the common emitter base characteristic are sufficient for obtaining the required information. And now, you can say the Bjt as a Pnp transistor, it is a common base, you can say common base here, and you have a 2 signal with respect to input terminal of BE, where you give a typically the kind of biasing, and then this is common emitter, emitter is common, and you have a signal for base and output is collector current, and here it is a common collector, and you have input output with respect to the emitter and base like. And now, this is a summary of qualitative summary of the all 3 configurations. So, we can say characteristic common base, common emitter and common collector. And so, input impedance for common base is low, and for common emitter it is medium, and of course, common collector it is high, and output impedance for common base it is very high, and common emitter high, and it is low for common collector, and phase shift it is 0 and 0 for common base and common collector, but for common emitter it is 180 degree, and voltage gain is high for common base and medium for common emitter and low for common collector, and current gain is quite low for common base, medium for common emitter, but high for common collector, and typically power gain is low for common base, but very high for common emitter and medium for common collector, and that is the reason it is common base configuration is used as a pre-amplifier and common collector is used as a buffer, but common emitter is the most common where it give a very high power gain. So, it is used all for power application with this configuration like. So, coming to some of the applications. So, here it is a transistor work as a switch for this LED. You can just see with the transistor. So, transistor can be used as a solid state switch for the use of switch in the transistor is operated in 2 modes like a saturation closed switch and cutoff region like open switch, and the behavior is similar to that a single pole double throw switch of this like how for LED glowing. When signal is there, the LED is glowing, and when signal is open, it goes cut off, then it is open. So, the transistor as a switch we operate cutoff state, where you do not give any signal there, input is grounded at 0, you can just see here, and the VC is less than cutoff 0.7 volt, both emitter base junction, collector base junction both are reverse bias, and transistor is fully off acting open switch, and the collector current IC 0, and hence the output voltage is equal to directly supply voltage VCC, and as you can see it here in the open circuit. And the second state is like a saturation state, where you give the signal, you connect the input, you bias with the input supply. So, base emitter voltage is greater than the cutoff in 0.7 volt, and both base emitter junction and base collector junction both are forward, and the transistor is fully on and operates as a closed switch, and the collector current is maximum, and V out is typically kind of 0 here, because it is connected to the ground. And this is typically application as a transistor amplifier. So, you are giving a signal here with the biasing, and that this signal of like a kind of varying time signal, maybe sine wave, it get amplified, and this is the circuit how it is goes work as a amplifier. A small signal, maybe a changing signal is applied, and that get amplified and goes to the your typically as amplifier, maybe the kind of loudspeaker or some kind of instrument like. And this is typically how the your voltage follower use typically the configuration with the so this is typically one common emitter configuration. This is the common collector configuration, how it is taking place as amplifier, and this is with the common base as a kind of amplifier, transistor amplifier. And this is typically the Darlington amplifier. This is your differential amplifier, and this is for your push pull amplifier. This is also used in many circuit as a kind of push pull amplifier, like you want to amplify the transistor as a amplifier. Well, another application of transistor is in logic gate. Because of the switch, it can operate as a switch, and you have a 2 transistor here, and you have a AB2 signal for these 2 transistor, and this is the typical truth table, that when you have a AB both 0, output will be 0, they are not typically connected. So, this since it is not connected, so it is output is 0, ground will go to here when 0 1. So, again even if you keep this as a 0 and it is 1, so this is not conducting, again even if it conduct, so you will not get. Similarly 1 0, so 1, and when both 1 1 both conduct, then only you will get this will be connected here. So, you will get the voltage here because of this resistance, and this typically represents as a AND gate, 2 input AND gate, and this is the truth table which designed by this transistor circuit of 2 transistor connected in series like. So, that work as a AND logic gate like. Similarly, you have a transistor as a logic gate here, 3 input AND gate. You can have a 3 input or maybe a 3 transistor cascaded as we have shown here. This is the chip which work as a 3 input logic gates, and these are the truth table here. These are the 3 input, and this is the output. The output is only 1 when all 3 are 1, remaining all remaining combination, you can call it output is your 0 only like. Then you have a typically transistor as a, you can call it as a logic, that both transistors are connected in parallel. So, when you have given a signal to 1, so it will be 1, only when both are 0, then only 0, remaining 3 combination will be 1 1 here, whether you are switch on, you switch on this, or both switch on, remain output goes to high, and this is how it is, we call it 2 input OR gate here, and this is the logic table, that only any one of the input is high or both are high, that you get 1, only one case when both are low, that you get 0. So, this is the expression, we call it Boolean expression Q equal to A plus B, here for this OR logic gate, and this is your 3 input OR logic gate, and here we call it like a typically Q equal to A plus B plus C, and this is the truth table. Then output most of the time high when any one of the high or all are high, only one case when all 3 are low, then only you get low, and this is the IC chip which is available for this as a logic gates like developed by using this different combination of the transistor. And this is the third logic gate, that is not, this is just invert amplifier with the, we already talk about common emitter. So, you give a signal here, when it is on, this will be grounded, so you will get 0, when it is off, you will get here 1, and this is we call it NOT gate here, and this is the logic table of NOT gate, and how it is the truth table of NOT gate. And this is your NAND gate. Here typically we call it both transistor again in series, but output now from bottom, it is from top, and any one of the 2 is either 0 or 1, you will get 1 here. If none of one of the any one of not conducting or both are not conducting, you will get high, only one case both are high, then only it will. So, it give you a signal corresponding to these are the IC chip, this we call it NAND gate, and the Q equal to A dot B inverse, and this is the logic table of this NAND gate. You might have already gone through. So, in all 3 cases are only one case when both are input 1, then only you will get 0. So, both are on, means both transistor conducting. So, this will be grounded like. Now, this is your NOR gate, here both transistors are connected in parallel. So, if any one of the 2 are on or both are on, you will get connect to ground. Only one case where both are off, you will get high, and this is the logic table here. When both are 0, you will get high, remaining 3 cases you are get, and this we call it Boolean expression q equal to a plus b bar, and this is the symbol of this your NOR gate like on, and this is the IC chip available for this NOR gate. Multiple NOR gate are there in the single chip like on. So, these are the some of the you can call it application of it. Now, coming to numerical problem of it. So, first numerical in Npn transistor 10 to power 8 holes microsecond move from the base to the emitter region, while 10 to power 10 electrons move from the emitter to base region, and emitter reads the base current as I b equal to 16 microampere, determine the emitter current and collector current like in this configuration like. So, we can say I emitter is the typically you can call it this your majority carrier minus the minority carrier. So, from taking a reference and putting the value, you get the your emitter current equal to 1.610802 milliampere, and further from KCL we can say IC equal to IE minus IB, putting the value of this you get collector current 1.602 milliampere. Therefore, emitter current IE 1.618 milliampere and collector current is IC 1.602 milliampere. And you can find out even the alpha from here typically. So, coming to second example, for the previous example data given here, find the alpha beta if the leakage current flow to the holes is considered negligible, and the describe the flow of current. So, here it is an Npn transistor shown here, and IB equal to 16 microampere, I equal to 1.618 and IC equal to 1.602, which typically given here, and from which we can find out if we assume IC equal to 0, then we can get alpha IC upon I minus IB upon this, and putting the value we get 0.991, and beta IC upon IB, I minus I beta this, and putting value it gets like 100. So, this is the current gain you get quite high like order of 100, and beta equal to alpha. So, 1 alpha give the same result, and this is again we get alpha equal to 0.9901 and beta your 100.125. Now, coming to third example, a BJT have alpha equal to 0.99 and IB equal to 25 microampere, ICB equal to 200 nanoampere. Find the following parameters: the DC collector current, the DC emitter current, and the percentage error in the emitter current when the leakage current is negligible. And given the data here, already alpha equal to 0.99, base current IB equal to 25 microampere, and leakage current ICBO to 200 nanoampere. So, putting the value here with alpha equal to 99, beta is alpha upon 1 minus 99. So, putting the value it comes 99, and collector current I beta IB plus beta plus 1 ICBO. So, putting the value we get typically collector current 2.495 milliampere, and the DC emitter current IC minus ICBO upon alpha, putting the value we get 2.52 milliampere, and neglecting the leakage current we have given emitter current error IC equal to beta IB, and putting the value it goes 2.475 milliampere, and I equal to IC upon alpha. So, it is a 2.47.99, that is 2.5 milliampere, and of course, the you can find out the typically the current gain 2.5 from this. So, it comes 0.793. Now, coming to example 4, a germanium transistor with a beta equal to 100 has a base to collector leakage current of ICB of 5 microampere. If the transistor connected to common emitter of configuration, find the collector current IB equal to 0 and IB equal to 40 microampere. So, coming to A part, with the IB 0, only the emitter collector leakage current flows and the leakage current are related ICO equal to beta plus 1 ICBO, and from here we can putting the value it comes 0.505 milliampere, and writing the collector current in the form of beta. So, IC equal to beta IB plus beta 1 plus ICBO, putting the value it comes 4.505 milliampere. Coming to question this problem 5, a transistor with alpha equal to 0.98 and ICB equal to 5 microampere is biased with IBQ 100 microampere. Find the IC and IE. So, solution beta equal to alpha upon 1 minus alpha. So, putting the value of alpha it comes 49, and ICO equal to beta plus ICBO, putting value it comes 0.9, and IC equal to beta IB plus ICO. So, putting the value it comes 5.15 milliampere, and I equal to IC plus IB, putting value it comes 5.25 milliampere. Now, coming to your problem 6, a transistor collector connected in the common emitter configuration shown here figure here, and see which is a very common configuration alpha equal to 0.9 and base current of 30 microampere. Find beta IC IE and assuming leakage the current 0. So, solution is beta equal to alpha upon 1 minus alpha, putting the value it comes 49, and for IC equal to 0, IC equal to beta IB, putting a value it comes 1.47 milliampere, and for ICB equal to 0, I equal to IC upon alpha, and it comes typically 1.47 divided by 0.8, it comes 1.5 milliampere. Now, coming to numerical 7, a silicon transistor connected in a common base common emitter configuration as shown here, which is very common configuration virtually for base current of 40 microampere and ICO equal to 0. So, if VB be equal to 6 volt, R equal to 1 kilo ohm and beta equal to 80, find the IE, RB, VC equal to 15 and RC equal to 3 kilo ohm, find VCQ. So, for first part we have to find out typically IE. So, we say alpha equal to beta upon 1 plus beta, putting value it comes 0.9876 and ICBO and ICO equal to 0. So, I equal to IB divided by 1 minus alpha, putting the value it comes 3.226 milliampere, and B part VB equal to IB RB plus VB plus IE RE. So, with VBQ equal to usual 0.7 volt for a silicon diode, so RB comes VB minus VB E minus IE RE divided by IB, putting a value it comes 51.85 kilo ohm, and with ICO equal to 0, so IC equal to beta E, putting the value it comes 3.2 milliampere, and then by using KVL from the collector, so VC equal to VCC minus IERE minus ICRC, and putting value it comes 2.174 volt like. So, coming to example 8, using the characteristic of figure 1, determine the resulting collector current with I equal to 3 milliampere and VC B equal to 10 volt. Using the characteristic of figure 1 given here, determine the resulting collector current if I remains the 3 milliampere, but VC reduced to 2 volt. Using the characteristic of figure 1 and 2, determine VB if I is equal to 4 milliampere and IB equal to this. So, from this characteristic, I mean we can typically find out here the characteristic indicate IC equal to I, that is 3 milliampere, and the effect of changing VCB is negligible, IC continue 3 milliampere, and from figure 1 IC 4 milliampere and figure 2 resulting VB 0.74 volt. Coming to example 9, using the characteristic of figure, determine the IC for IB 30 milliampere and VC 10 volt, and using the characteristic of figure, determine the IC at IB at VB equal to 0.7 and VC equal to 15 volt. These are the characteristics given, and from this we can find out at intersection IB equal to 30 milliampere and VC equal to 10 volt. So, for which IC comes 3.4 milliampere, and from figure B we obtain IB equal to 20 milliampere intersection of VB of 0.7 and VC of 15 volt between VC 10 volt and 20 volt. From figure we can find out IC equal to 2.5 milliampere at the intersection of IB equal to 20 milliampere and VC 15 volt. Coming to example 10, a Bjt controls power from DC source of 200 volt to resistive load on this as a kind of regulator of for this load condition, and with the transistor incision of Bjt voltage is your 1.1 and base resistance of chosen 2.5, such that there is a overdrive. If the base source voltage is 10 volt, then the base to emitter voltage is VC 1.8 volt. For the on state, determine the force current gain beta and then the power loss in the Bjt. I mean we are operating in this region like. So, we can say referring to figure, we can say IC equal to Vs minus Vc by R, putting the value 200 minus 1.1 divided by 4. So, it comes 49.7 ampere, and for the base drive IB equal to VB minus Vc divided by RB. So, it is a 16.4. I mean, so you can find out the force current gain is only beta F equal to IC upon IB, that is 49.7 divided by 16.4, that is 3. In the steady state condition, the Bjt power dissipation is P equal to VC IC plus VB IB, putting the value it comes 84.2 watt, and the overdrive the power dissipation is not significant. So, the steady state efficiency of Bjt is eta equal to output upon output plus input. So, just putting value of output and divided, this comes 99%, and power switching by means by Bjt appears to be inefficient. Now, there are some unsolved problems similar to, I mean which you can exercise, and these are the you can say text or books from which this lecture is developed, and thank you very much.